Okay, now since that we've learned the rules for our four quantum numbers, which describe the location of electrons around a nucleus, what I'm going to expect for you is certainly that you are intimately aware of the rules, the allowed values of all the quantum numbers, including their start and stop values relative to the other quantum numbers or just relative to the numeric scale itself. You should know exactly what the quantum numbers can be and what values they're allowed to take exactly. Then what the next several slides here are going to demonstrate is applying the ideas of the quantum numbers to make predictions about the behavior of electrons based on what quantum numbers are allowed. So let's begin with this first problem, which says, on which energy level does an m orbital first appear? Okay, so m is a letter designation for a certain value of angular momentum. And what you see there is I list L values beginning at their start point of 0 and then up through the first 9 digits of integer value. And then below them, I'm listing the corresponding letter designations that apply to those letters. The first 4 from L equals 0 to 3 are the familiar SPDF, which are the orbitals that all elements in the periodic table use to build their electronic structures. Then after orbital F, the orbitals go alphabetical with the exception of J. J is left off, and again, let's not get into the gore in detail as to why. It comes from another application that was applied with J. So we will leave J out, so that means that we go G, H, I, K, L, M for the remaining letters. Now, L is allowed values of 0, 1, ... up to n minus 1. So the m orbital first appears when L is equal to 9, and L is equal to 9 when n, according to the rules, would be equal to 10. So on energy level 10 will be the first appearance of an m orbital. Of course, on every level above 10, there will be an m orbital. So how many total electrons could you place? This time I'm asking how many could you place in an h orbital. Now you could use this same idea to determine how many electrons could be placed in an m orbital. So this time I said how many can be placed in an h orbital. H corresponds to an angular momentum, a quantum of angular momentum of 5. To find out how many orbitals are, what we're going to need to do is know the degeneracy of an h orbital. And then we will doubly occupy those h orbitals once we know the degeneracy. So to find the degeneracy of the h orbital, we will take the fact that L equals 5 for an h orbital, then we will turn to m sub L for the number of orbitals that corresponds to. Or we could use the rule that the degeneracy of any orbital is 2 times script L plus 1. With L equal to 5, 2 times 5 plus 1 is equal to 11. Or from the m sub L values, they start at minus 5, go through 0, and go up to plus 5, and that counts out 11 orbitals. Now, since in each orbital, you can doubly occupy them with a spin up and spin down electron, put 2 electrons per orbital, that means an h orbital could hold 22 electrons. Let's look at quantum number example 3. Based on the following electronic representation, can you list the 4 quantum numbers that this picture and the designation under it shows? Well, we see a line with a 6S, and on that line is an up pointing arrow. We're supposed to use that picture representation to determine the 4 quantum numbers that are represented. Well, S, of course, is an S-type orbital of angular momentum 0. So the S implies L equals 0. The 6 in front of the S means you're on energy level 6, so N is 6. The upward pointing arrow is an indication that it is a spin up electron with M sub S equal plus 1/2, and all orbitals of no angular momentum where L equals 0 also have M sub L equals 0. So the four quantum numbers of 3a are n equals 6, L equals 0, m sub L equals 0, m sub S equal plus 1/2. In 3b below, we have a line showing underneath 4d, and then there are 5 numbers designating the equal energy lines of each of these d orbitals. And of course, the d is an L equal 2 orbital. When L equals 2, m sub L goes from plus 2 down to minus 2, including 0. There are 5 of them, so that's why there are 5 lines shown. We can only assume the numbers under each line are the m sub L values of each of those particular orbitals. So there's a downward pointing arrow on the line designated -1. So with that information, I'm going to say that since the letter in front of the D is a 4, that n equals 4. Since it's a D, it has to be an angular momentum 2 orbital. And because the fourth box over, with the -1 designation has a line on it, I'm going to say m sub L equals -1. And since the arrow is pointing downward, m sub S equals minus 1/2. Question 4 here asks you to determine what is wrong with these designations. So something is incorrect with the designation for A of 2D3. So let's try to figure out what could possibly be wrong with a designation, orbital designation 2D3. First of all, you should note that a D can hold upwards of 10 electrons because L equals 2, and the m sub L degeneracy is 2L plus 1. That means that there are 5 orbitals of that L equal 2 value, and they could each doubly occupy. So there's a maximum of 10 electrons that can go in, so that can't be the issue. But what is the issue is that when we, according to this designation, L is 2, but energy level N is 2. And according to the rules of quantum mechanics, when L is equal to 2, the first orbital energy level where L equal 2 appears is N equal 3. So you cannot have a 2D orbital. The first possible D orbital is a 3D orbital. So the designation 2D superscript 3 is incorrect. In case 4b, we see that we have the designation 4s superscript 3. Well, let's first decide about the N and L values and if they're valid. N is 4, so we're on the 4th energy level. S corresponds to an L equals 0. And L equals 0 is allowed on energy level 4. As a matter of fact, you're allowed L equals 0, 1, 2, or 3 on energy level 4. The problem with this designation lies in the fact that the superscript is 3. And because L is equal to 0 for an s orbital, that means m sub L is 0 for an s orbital, or the s orbital is non-degenerate. And non-degenerate orbitals can only hold a spin up and spin down electron of m sub S plus 1/2 and minus 1/2. So you can only occupy 3 total electrons in an s orbital, so this is invalid as well. Let's explore several examples where I give you the quantum numbers and you tell me how many electrons could possibly simultaneously possess those quantum numbers. So in question 5a, I ask how many electrons on an atom can simultaneously possess, in 5a, the quantum numbers n equal 3 and L equal 2. All right, first of all, we should note that they are valid because L range can be available on orbitals of up to n minus 1. So this is representation of a 3D orbital, and you should be able to tell from the fact that it's a D orbital that it should be able to hold 10 electrons. And that would be because when L is 2, I can have m sub L values that give me a degeneracy of 2L plus 1 or 5. There's 5 degeneracies. to the d orbital, 5 equal energy cases. Each can be doubly occupied with an m sub s plus and minus 1/2 electron. So that's 5 times 2, or a total of 10 electrons, is the answer for 5A. Now what about for 5B? I'm told I'm on energy level n equal 4, and I want to know how many electrons on energy level n equal 4 could possibly have m sub L equal to 0. Well, first we should note that on energy level 4, you can have a 4s, a 4p, a 4d, and a 4f, because the L values that are allowed on n equal 4 begin at 0 and go to L equal 3. So that's begin at S, go to P, D, and then end at F. Now, each of those has an m sub L equals 0 orbital, but each of those has only one m sub L equals 0 orbital. Of course, the 4s does, because it's the only m sub L value it has. The 4p has m sub L's from +1 to -1. The 4d has m sub L from -2 to +2. The 4f has m sub L's from -3 to +3. But each of those p, d's, and f's have an m sub L equals 0. Now this m sub L equals 0 orbital, there's no specification as to the spin of the electron. So then technically, 2 electrons could be in there, each, because there's no designation of what you specify for the m sub s value. So you can have 2 in the m sub L equals 0 for the s, 2 in the m sub L equals 0 for the p, 2 in the m sub L equals 0 for the d, 2 in the m sub L equals 0 for the f. So a total of 8 electrons can occupy these 2 quantum numbers simultaneously on any atom. In case 5C, the quantum numbers you're given that electrons possess on a particular atom are that n equals 2 and m sub s equals -1/2. Now, the m sub s equals -1/2 means I have a spin down electron. So what we need to know is how many spin down electrons can fit on energy level 2. Well, on energy level 2, you're allowed 2 orbitals and 2 orbitals only. They would correspond to L equals 0 and L equal 1. L equals 0 is an S, L equal 1 is a P, and the P is triply degenerate because m sub L can be -1 to +1. So there are 3 p-type orbitals and 1 s-type orbital on energy level 2. Each of those is allowed to hold a single spin-down electron. So a total of 4 electrons can simultaneously have n equal 2, m sub s equal -1/2. In case D, we say, okay, we're given that n equals 3, L equals 1, m sub L equals +1, and m sub s equals +1/2. So we are given 4 quantum numbers. First, you should note that they are all valid, because when n is equal to 3, L is allowed to be 1. When L is equal to 1, m sub L is allowed to be +1. And of course, m sub s is allowed to be +1/2. Now, to figure out how many electrons can simultaneously have that, we should recognize this is a statement of essentially the Pauli principle. No 2 electrons on the same atom can have 4 of exactly the same quantum numbers, because you'd be putting those electrons in the exact same location. Only 1 electron can have 4 unique quantum numbers. As a matter of fact, you can see in the picture below, I'm zeroing in on that electron. I have energy level 3, and I show the 3 levels available, or orbitals available on energy level 3. I zero in on the L equal 1 orbital, which is the 3p. I zero in on the m sub L equal +1 orbital of that L equal 1 p orbital. And then I in particular put a box around the m sub s equal +1/2 electron on that designation that has those 4 quantum numbers. Let's look at case 5E. How many electrons on an atom can simultaneously have n equal 4? Well, I'm only given n equal 4, no other information. So I have to assume that I want to know something about all electrons that have n equal 4. So essentially I need to know how many electrons fit on energy level 4. And when n is equal to 4, L also can take 4 unique values: S, P, D, and F. I can have a 4S, a 4P, 4D, and a 4F. And they go up to 4F because when n is 4, L stops and caps at L equals 3, and that is the F orbital. So now, based on my rules we've discussed previously, the non-degeneracy of the S tells me I can put a total of 2 electrons in it. The P is triply degenerate, and each can hold 2, so that's 6 electrons for the P. The D is 5-way degenerate, so you can put 2 in each, that's 10. And the F has 7 degeneracies, with 2 electrons each, makes 14. So 14 plus 10 plus 6 plus 2 gives me 32 electrons on an atom, can simultaneously have n equal 4. Okay, next we're told, what if we have the case n equals 6, L equal 4? Now, I'm sorry, there's 3 quantum numbers I'm designated. N equals 6, L equal 4, M sub S equal plus 1. First, they are all valid with one another because when n is 6, L is definitely allowed to be 4. So the main thing I need to recognize here is I want only the spin-up electrons that can occupy the L equal 4 orbital. So what is an L equal 4 orbital? Well, in letter designation, it would be what I called a G orbital, because S is 0, P1, D2, F3, G4. Now, the L equal 4 orbital has a degeneracy of 2 times 4 plus 1, or 9, meaning the M sub L's go from plus 4 down to minus 4. There's 9 of those orbitals, and if I put a spin-up electron in each, a total of 9 electrons can simultaneously have n equals 6, L equal 4, M sub S equal plus 1. Okay, what about case 5G? What if I have n equal 4, M sub L equal minus 1? Well, this is the contrast, the one above where I had n equal, I'm sorry, I didn't see that correctly. N equal 4, M sub L equal minus 1. So I'm again on the 4th energy level, but now I want to zoom in on only the orbitals that have M sub L equal minus 1 on energy level 4. So I have an S, a P, a D, and an F. S's have no M sub L equal minus 1, but P's have an M sub L equal minus 1, D's have an M sub L equal minus 1, and F's have an M sub L equal minus 1. Since there's no spin quantum number designated, I can have a spin up and a spin down orbit electron in M sub L equal minus 1. So that means I can have 2 in that M sub L equals minus 1 P, 2 in the M sub L equal minus 1 D, 2 in the M sub L equal minus 1 F, for a total of 6 electrons simultaneously having n equal 4, M sub L equal minus 1. One last page of these examples. Let's take example 5H. How many electrons can simultaneously have n equals 3, M sub S equal plus 1/2? So this is the spin-up electrons. We're saying how many spin-up electrons can go on energy level 3. So now we need to determine how many individual orbitals are on energy level 3. And when n is 3, you're allowed 3 orbitals. The L equals 0, 1, and 2. So you're allowed a 3s, a 3p, and a 3d. Now, in the s orbital, since it's non-degenerate, you can put 1 spin-up electron. The p orbitals are triply degenerate because 2l plus 1 is equal to 3, and you can put a spin-up electron into each of those, so that's 3 more electrons. The L equal 2 electrons have 2 times 2 plus 1, or 5 degeneracy, so D's have 5 at a time. And you can put 1 spin-up electron in each of those, so I will have a total of 5 plus 3 plus 1, or 9 electrons simultaneously possessing n equal 3 and M sub S equal plus 1/2. Then finally, for example I have n equal 4, M sub L equals 0, and M sub S equal minus 1/2. And now, let's be clear, on level 4 there are 4 different orbitals, each of them having an M sub L equals 0. The S has m sub L equals 0 possible. The P, the D, and the F all have m sub L equals 0. But I don't want both electrons in this m sub L equals 0 orbital. I'm specifying I only want the m sub S equal minus 1/2 or downward electron. So that is one electron can have those three quantum numbers in simultaneously on that level for each orbital. So that's a total of 4 electrons allowed with those quantum numbers. All right, we're ready to look at the electronic structure of multi-electron atoms beyond hydrogen. Now, before we do so, we got to discuss one of the nuances that kind of makes the applications of quantum mechanics a little bit weirder than they even seem so far. What actually happens, as we talked a little bit about previously, was that hydrogen is the only atom which can be analytically solved, exactly solved, get exactly the right answer. Now we can mimic numeric solutions using computers and get very close to the right answer for any atom that has more than one electron, but you can't analytically solve it. And what it means to be analytically solved is you can get an equation. The answer, the solution to the problem gives you equations, and then you can look at the equations, plot the equations, think about the behavior of those equations, and use them to describe what goes on. And so what happens in the hydrogen atom that turns out to be problematic for the many electron atom is the fact that the energy of an orbital is controlled solely by principal quantum number n. All energetics of the orbital depend on n and depend on n only. So what this means is when there are the opportunity for orbitals of multiple angular momentum to appear on a given energy level, all orbitals of the same on the same n level, on the same principal quantum number level, have the same energy. That is whether or not they are an S, a P, a D, or an F. So the graph I'm showing at the bottom of this page is depicting, for the hydrogen atom, the solutions say that the energy depends only on the principal quantum number, so that on energy level 1, where only the s orbital is available and it's non-degenerate, there's only a single orbital on that level. But now when we go to energy level 2, where L can be either 0 or 1, meaning there can be 2s or 2p, and the 2p is triply degenerate, there are now 4 equal energy orbitals that hydrogen predicts would exist on energy level 2. Likewise on energy level 3, now there's 3 orbitals available, a 3s, a 3p, and a 3d, and I show them on a line of equal height on the energy scale. That's because according to what hydrogen says, they are all equal in energy and would equally likely be populated if this pattern fit for a many electron atom as well as it does for hydrogen. Then finally I show on energy level 4, there are 4 unique kinds of orbitals available. I show lines depicting those orbitals and their degeneracies. So all of those orbitals, technically, according to what hydrogen predicts, should be of exactly the same energy. This is not what we see when we go to actual many electron atoms. So let's try to explain on the next few slides what the difference is between this picture and what we actually see for the many electron atom. In order to describe the discrepancy that many electron atom electrons experience compared to the solution quantum mechanics predicts for the 1 electron hydrogen atom, we need to introduce a couple new concepts, including what is known as nuclear shielding in the many electron atom. So first of all, what we will say is that in a many electron atom, if you have a different L value on the same n level, unlike the hydrogenic you are going to have a different energetics that you feel due to the presence of other electrons around you. See, that's not, when you solve the hydrogen atom, you don't have these other electrons to introduce these kinds of effects. So let's first differentiate the electrons into two different classes of electrons, and we'll use these two different classes throughout the rest of our discussion this semester. First, we'll talk about core electrons. Core electrons are the so-called inner electrons. They are in what we will say are those on completed energy levels. So if you look at where an atom resides in the periodic table, and you look at the row that it happens to be sitting in, that is an incomplete row. You haven't finished off electrons in that energy level yet. So what we will then do is say that all electrons in completed rows are in shells of electrons inside. Remember, those in the completed rows will have lower n values. Lower n value means in closer to the nucleus. So these electrons will all be closer to the nucleus than the electrons that are being populated in the n level that we are speaking about. That is the row that is not completed yet in the periodic table. So the core electrons are all in completed rows. You count up those electrons. Then we will differentiate the others as valence electrons. Valence electrons are in the incomplete row. They're in the outermost energy level of the atom. They're furthest from the nucleus. They have the highest n value. They are therefore the highest energy electrons, remember, meaning the least negative energy electrons, and they are furthest from the nucleus. Turns out these are the easiest to access energetically. I can pluck these off most efficiently because it takes the least amount of energy to pull them loose. Now, I just said they are the highest in energy, but remember, in this weird designation, the highest in energy means the least negative in energy. So they're the least tightly bound of the electrons on the atom. And so therefore, they're the easiest to pull loose from the atom when they're in this valence level. And in another regard too, if you're going to add electrons to an atom, you would add them to the valence level. This is energetically the cheapest place to place any electrons you wanted to add to an atom. And what we're going to see going forward is all the action takes place at the valence level. This is where all the electrons are either going to be added or removed and swapped and traded, shared, and all these other things transferred. All the things that atoms want to do with each other. We'll focus on these valence electrons, the outermost electrons, the ones in the incomplete row, above and beyond the core electrons. So then what we will say then is we will define something called the valence electron effective nuclear charge. For all electrons on the valence level, we say that that is equal to Z effective, and it is equal to Z minus the total number of core electrons, where Z is the atomic number of the element. So I will take the atomic number of the element, figure out how many electrons are in completed rows, subtract that from the atomic number, and that'll give me the effective charge. And what we're saying is that the core electrons are blocking most of the nuclear charge. The outermost electrons only get the leftover charge that isn't being taken up by the core electrons, and that will be represented by this value that I'm calling Z effective. Let's look at some examples of finding Z effective for the valence electrons in group 1 elements. Group 1 elements are column 1 elements headed by hydrogen, and then followed by lithium, sodium, and so forth. So let's go to lithium. Lithium is in box 3. That means Z is equal to 3. And if we count the core electrons, those are the lithium valence electrons are in row 2. The lithium core electrons are all those in row 1, and there are 2 total electrons that represent the core electrons. So Z is equal to 3 minus 2, or Z effective is 3 minus 2, or 1 for lithium. Let's go to rubidium, which is element 37. It has Z37, therefore. It has 37 protons in the nucleus. And then if you count up an electron representing all the completed rows of the table, the completed rows of the table will go to krypton, which is 36 electrons. Z effective for rubidium, 37 minus 36, is 1 as well as lithium. Go down to francium, element 87. So it has 87 protons in the nucleus. Its core electrons are represented by the completed rows of that above francium, which are the 86 electrons before it. So Z effective for francium is 87 minus 86, or 1 as well. So what we're seeing is all these group 1 elements that we've checked on have a Z effective of 1. The valence electron, the single valence electron of all group 1 elements, sees an effective charge of 1. The other 86, or the other, I'm sorry, not just 86, that would only be true for francium, but for all the other elements as well, their lone valence electron in the outermost energy level, it has a leftover charge of 1 positive charge from the nucleus to interact with that nucleus. So essentially what we can think of then is that francium is like a giant hydrogen atom where the inner electrons are blocking all the charge except 1 charge. Cesium above it is a giant hydrogen atom where the inner electrons are again blocking all but a positive charge of 1, and so forth. So it seems then that it wouldn't be surprising that all elements in column 1 are chemically similar. If we could just continue this theme with column 2, we would see, for instance, for beryllium, which has Z of 4, it still has 2 core electrons. Beryllium has Z effective of 2. Magnesium, which has Z equal to 12, has 10 core electrons. It has Z effective of 2 as well. So does calcium, so does strontium, so does barium. They all have the same Z effective. And as a matter of fact, as the statement claims at the bottom, all elements in the same group, or that means all elements in the same column, have the same Z effective. That is the leftover charge that the valence electrons experience after the core electrons have each taken up some of the charge each. Now, where this gets weird is when you go over to, say, column 16, headed by oxygen. Oxygen is element 8, and oxygen has a total of, as you can see, 8 for its Z value, and it has 2 for its core charges, because only row 1 is completed above it. So Z effective of the 6 valence electrons for oxygen is 6. Now if you go down to sulfur, you would get the same thing. You count up its element number 16, and it has 10 core electrons. So Z effective for the 6 valence electrons of sulfur, the 6 electrons in row 3, are 6. But now if you went down below sulfur to selenium, it wouldn't seem as if you would get 6 for the valence electrons that are left over. If you do selenium, you would get a total of 16 for Z effective. So it seems like that something is weird going on there. Let me assure you that selenium, just like sulfur and just like oxygen, has a Z effective of 6. So the discrepancy that you would get from solving the little equation for the core electrons is something we're going to have to discuss after we understand a little bit more about what are really core electrons and what are really valence electrons for an element like selenium. So let's table that for the moment, and let's just for now blindly apply the statement at the bottom that if you are an element in the same column as other elements above or below you, then you have the same Z effective, or your valence electrons feel the same effective nuclear charge due to the shielding, we will call it, of the core electrons from all of the positive charge of the nucleus. Now let's describe how s electrons on level 3 can have a different energy amount than p electrons on level 3. Even though quantum mechanics predicts if you are a lone electron, you should have the same energy if you're in orbital 3s than in 3p. Now the effect of many electrons is going to alter the energy of 3s compared to 3p. And in order to see this, what we plot is a picture of the so-called probability density of the likelihood of location of an electron riding the 3s ride, or in the 3s orbital. Quantum mechanics gives us a so-called wave function. From this wave function, which is an analytical formula, we understand how to interpret location of the electron from the form of this function describing an electron in the 3s orbital. If we make a plot of the likelihood of location, which we call the probability density of this 3s electron, it turns out we get several humps of probability. And these humps reveal the likelihood of the electron being at a certain distance r away from the nucleus. Now, what you find is that a huge hump exists where the electron is most likely to be found. However, there are two tinier humps in a region at much shorter distance r than that huge hump. And it turns out if you measure that distance r for those tiny humps, it says that the 3s electron has a possibility of penetrating into the core region and being underneath the shielding of all electrons on energy levels 1 and 2. So effectively, a 3s electron gets to feel a little more of the positivity of the protons in the nucleus, because there is times and chances for it to penetrate inside the distance that most electrons spend for the 3s electron. Now, this is just a very weird phenomenon. It's very weird in the sense that the electron isn't exactly where you think it is all the time. We're saying here, the quantum mechanics says it gets a little chance to spend a little time in the core, even though it's really on the valence. So when it's in the core, it will feel more pull from the nucleus, and therefore will experience a slightly lowered energy. So this penetration of the core shielding allows for a 3s electron to have a little bit lower energy than would be expected due to the shielding of those core electrons. These three graphs simultaneously plot the so-called probability densities, or likelihood of occurrence positioning, of all three possible angular momentum values on energy level 3. Those, of course, would be 3s, 3p, and 3d. Now, what we're showing again are that the maximum humps of 3s, 3p, and 3d orbitals are all essentially the same distance from the nucleus. Essentially. So all energy level 3 electrons spend the vast majority of their time at the same distance out from the nucleus, whether you're in a 3s, whether you're in a 3p, or whether you're in a 3d. But what we do see in addition to that is that the 3s orbital with that little hump inside has more likelihood of, has a little bit of likelihood of also being at that r distance out. So it has more possibilities of being closer to the nucleus than either a 3p or a 3d electron. The 3p also has a hump inside that allows it to have more likelihood of being inside the core and therefore experiencing more positivity than does a 3D. And then so the 3D, it turns out, is higher in energy for a multi-electron atom than a 3p. And a 3p is higher in energy than for a multi-electron atom that has a 3s available. So now what we will just conclude with a statement is that when you have many electron atoms, core electrons shield the valence electrons from seeing all the positivity of the nucleus, but orbitals in s penetrate the core most effectively, so have lowered energy than do the p's and the d's. Orbitals in electrons in p's penetrate more than d's, so they will have a lowered energy relative to d. And if you were on energy level 4, electrons riding orbital d can penetrate the core more effectively than f orbitals, so they would have separated and lower energy than f orbitals would. So, as a result of this penetration of the core by valence electrons in an s, it lowers their energy relative to a p, a d, or an f. And likewise, the p also has some penetration, not as much as an s. So on energy levels where all 4 of these types of orbitals are available, the p with a slightly more penetration than d or f, but less than s, means that p will have lower energy than d or f, but not as low as s. And likewise on this level with all 4 available, the d will penetrate inside the core a little bit more than f, therefore seeing more positive charge, therefore lowering the energy of electrons in d's, so they will be lower in energy than f orbitals, even though a hydrogenic one electron picture doesn't predict this. So if we then make an energy scale and on it plot all orbitals up through the first 5 or so energy levels, what we will see is that the s's and p's and d's and f's now separate from one another. Now notice the m sub l degeneracies remain intact. For L equal 1, m sub L can be 1, 0, or minus 1. The 3p orbitals remain degenerate. Likewise, the 5d orbitals remain degenerate. And the 7f orbitals would remain degenerate. But you now have this ordering that the 1s fills, then you go to energy level 2, but because of penetration of the s on level 2 compared to the p, the 2s will fill before the 2p. They are not degenerate as the hydrogenics would predict. After you fill the 2p completely, you have to go to energy level 3. There are now 3 orbitals available, 3s, 3p, and 3d. The penetration of the 3s makes it lower, the 3p next lower, the 3d highest. But something bizarre, even more bizarre, happens. And that is the fact that the energy level 4 s orbital has so much penetration of the core that it lowers the energy of that s orbital even below an energy level 3d. So a 4s slides in below a 3d, even though 4s is on a higher n level than the d orbital is. So we have this weirdness of the ordering becomes even more exacerbated by penetration of the core. This even gets worse for the f orbitals. When you start to put the f orbitals in, they are penetrated by several other orbitals before they get to fill. So the bottom line is, how can you keep an order for these orbitals with these weird penetrations so that you can just recognize from how many electrons are possible which orbitals they would occupy and in what order they would occupy them. What we'll do on the upcoming slides is show some tricks as to how to properly order the configurations of filling electrons for many electron atoms. So, a memory device that can be used to help you figure out the ordering as to how to fill the electrons properly into a many electron atom is done as follows. As it says here, first lay out all possible orbitals on each energy level in a triangular form as you see there. Start at the top. On level 1 you can only have a 1s. On level 2 you can have 2 orbitals, 2s, 2p. Level 3, 3s, 3p, 3d. 4s, 4p, 4d, 4f. Under that, then you make a 5-member triangle going out to G, a 6-member triangle going out to H, a 7-member triangle going out to I. So you have this basic shaped triangle that you would see from those. Next, go diagonally through those rows with the red arrows as seen so that it catches every one, that you don't leave any blank, you catch every one. You go diagonally through and you see how that works out to catch all the various orbitals. Then start at the top arrow to its tip and then go to the second arrow to its tip, third arrow to its tip, and those show you the order of filling. So at the very bottom it shows you fill the 1s, then the 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d. This gives the proper order of filling, at least for the first several rows. Now eventually this even breaks down when you get to the higher levels, but for the atoms that we want to put electrons in, this will do the trick for us. So the only remaining task is to fill up those orbitals according to the Aufbau rule, meaning you put the lowest energy orbitals filled first, and so you just populate them with the maximum number of electrons they can hold. And we'll see some examples of that on some upcoming slides. So certainly you should commit to memory how to form this triangle and how to digest it in order to figure out the order of filling of the orbitals. Let's begin to populate the elements of the periodic table, and we'll start off by doing some things to remind ourselves about Hund's rule. So we'll use the box notation that we had used earlier last lecture in describing how Hund's rule worked. So let's begin with hydrogen through beryllium. Hydrogen element 1, beryllium element 4. We have 4 total electrons, and on the first energy level, which only has an s orbital, you can have only 2 electrons on the first energy level. That's why there's only 2 elements in the first row of the periodic table. So hydrogen with 1 electron, I will place an electron in a box representing the 1s. I can spin it either up or down. It's completely arbitrary. For helium, which has 2 electrons, using the Aufbau principle, in the ground state, I will place them in the lowest available orbital, which is orbital 1s. And I can have an up and down spin electron. So the electron configuration of helium is 1s2, or some people say 1s squared, but I prefer 1s2. Now, when we move to lithium, I'm putting the 3rd electron in. According to the Aufbau principle, I will go to the next available energy orbital. So I now have to introduce orbital on level 2. So 1s, the 1s is complete, that would be the core. 2s is the valence, or level 2 is the valence, and available on level 2 is 2 kinds of orbitals now, 2s and 2p. Now, based on the penetration and shielding arguments we just made, the 2s will populate before the 2p. I could also verify this using my triangle rule. I would go through the 1s diagonally, followed by the 2s diagonally. And so the 3rd electron will go into that 2s orbital, and I could again arbitrarily put it in spin up or spin down, and I have a box representing that as you see to the right. For beryllium with 4 electrons, its electron configuration will go in the Aufbau sense to the lowest slots, That'll be 1s2, 2s2, as you see. So that would be the electron configuration for beryllium. Let's continue using the Aufbau principle, the Pauli principle, and Hund's rule to populate the next 4 elements of the periodic table, those of boron through oxygen. Now, when we do these elements, we're going to need all orbitals available on energy level 1 and energy level 2. Of course, the energy level 1 orbitals are filled first, and that's only the s, and it's s can hold 2, so I'll have 1s2. Now I turn to energy level 2. Remember, those 1s electrons are core electrons for these elements. And because of the penetration of the core to the s on level 2, it's lower in energy than the p on level 2. So the s will get filled before the p. The s, again, is non-degenerate and can hold only 2 paired electrons. So for boron, it will have the 2s2, just like beryllium had. So boron contains the configuration of beryllium. But now for the 5th electron, we need to place it into a new available orbital, and on energy level 2, that would be the 2p. And showing, again, in reference to Hund's rule, I will have 3 boxes degenerate, and I'm only showing the p boxes for the Hund's rule for the boron. I have 3 boxes for those p orbitals, and I put a single electron in the boxes. Now again, I could have put that electron in any of the boxes, either up or down. But when I then go to carbon with 6 electrons total, the Aufbau principle says, of course, occupy the 1s first, the 2s second, just like was done with beryllium. There's a total of 4 electrons in those. Now I have 2 electrons to place in p. And remember what Hund's rule said, those 2 electrons should go into this atom in separate of the degenerate p orbitals with the same spin. And again, experimental evidence to back this up is that these magnets of these north poles aligning in such a fashion shows that carbon has some magnetic character associated with it. Moving to nitrogen with 7 total electrons. Again, the first 4 go into the 1s and 2s. Now I have 3 electrons to place in p, and again, according to Hund's rule, you populate them in separate degenerate orbitals of the same spin. So that would be as depicted to the right of the n in the boxes shown for the p only. Finally, when you come to oxygen, element 8, the first 4 electrons again occupy the s and 2s and 1s orbitals, excuse me. Now I have 3 orbitals to place into p. So now I am forced to come back and begin to pair. So one of the p orbitals has a paired set of electrons, while the other 2 remain using Hund's rule with electrons in separate degenerate orbitals spinning in the same direction. Okay, let's just now randomly skip around the periodic table. Let's take as a first example the element phosphorus. You see its location in the periodic table. It is in row 3, and it is, when you come across in row 3, it is the 5th element over in row 3. Notice there's kind of a big gap in the table, which we will attempt to explain here in a brief moment. But there's a big gap in row 3. The 5th element in row 3 is the phosphorus element. It has box 15, meaning 15 electrons. So what I would do is I would draw my triangle, and then I will put diagonals through those triangles, and then I will write down the order from tip to tail of the orbitals in those triangles, filling them appropriately with the proper amount of electrons they can hold. That would mean I'd begin with 1s and put 2 into it. I'd need to go to the triangles or the arrows again, come up with the next orbital along and the new arrow, the second arrow, which is a 2s. It can hold 2. I'm up to 4 electrons. If I stop here, I'm at beryllium. So I need to go to the next diagonal, which includes a 2p and a 3s. When I put those as the order of being filled next, p's with a triple degeneracy, putting 2 electrons in each, can hold 6. S holds 2. When I count that up, that would only be 13 electrons. I'm sorry, actually it'd be 12 electrons total to get to the 3s2. That's not enough, so I need to put another arrow, and I follow along that arrow, and it goes through 3p. But if I don't fill the 3p up entirely, if I did, that would be argon. I only want to fill that 3p up until I reach the maximum of 15 electrons that are required for phosphorus, and that would be 3p3. Now, if I did this with boxes, all the s orbitals you see would be filled with paired electrons. The 2p with 6 electrons would have 3 boxes, each containing 2 electrons, and the 3p would have 1 electron in each of the 3 degenerate boxes and would have those electrons spinning in the same direction, in deference to what we called Hund's rule earlier. Let's go to the example of, say, cadmium. Cadmium is element 48. Neutral cadmium would therefore have 48 electrons to populate. You'll notice from the periodic table shown that it is in the 5th row down, and it is the 5th row down and the 12th box over to the right is the location of cadmium. So what I will then do is begin to populate electrons all the way through that, and you will notice that it has 4 completed rows. Those represent the electrons through krypton, and then it has these 12 electrons in the uncompleted row level that we have to put in addition to those electrons, the 36 electrons completed for the krypton. So again, I draw my triangle, start going diagonally through it, and putting the maximum number of electrons into each of those orbitals until I reach 48 electrons. So I need to fill up that 1s, go to the second arrow, fill the 2s. On the third arrow, I have the 2p and 3s, and I fill those up appropriately with 6 and 2 electrons total. If I stop there, I'm only at electron 12, so I got to keep going. The next arrow introduces a 3p and a 4s, which gives me now a total of 20 electrons. If I would stop at the 4s2, got to keep going. So I come to the next triangular diagonal arrow, introducing a 3d, a 4p, and a 5s. Put 10, 6, and 2. That gives me 18 more. That gives me 38 total electrons so far. If I get to the end of 4p6, okay, that's where I would be. Actually, the end of it is not 4p6, it's 5s2. Excuse me. That's where I should have ended there. That's a total of 38 electrons when I get through the 5p2, if you add those up. So I need to go to the next available orbital. I come to the next diagonal arrow. The next orbital is a 4d, and the d can hold 10. So I populate that d entirely, and I now have the total number of electrons of 48. So this represents the electron configuration of cadmium. Let's look at forming the electron configuration of an anion. In this case, we'll take bromine. Bromine anion is actually known as bromide. So we'll take the bromide anion. A neutral bromine has 35 electrons. This particular -1 charged anion therefore has an additional electron to the neutral's case. So it has 36 electrons instead of 35. And therefore we would say isoelectronic, having the same number of electrons as krypton. So this, in addition to being the electron configuration of bromide, is also the electron configuration of neutral krypton. So once again, now I have 36 total electrons, including the extra electron for the -1 anion that I need to populate. So I just begin going through my triangular formation, filling them up to their max, 2 electrons per S, 6 electrons per P, and in this case I will need some electrons in the D as well. So I'll put the 10 electrons in the D that I need, and I start counting them up. 2, 4, 10, 12, 18, 20 when I get through 4s squared, and then I still need to continue onward, add in 3d, that's 30 electrons, then finally add on the 4p, and that will end me up at a total of 36 electrons by the time I get to the end of the completed 4p6. Now you will also notice in the periodic table I'm at the end of a completed row. We're going to make the connection between the periodic table and electronic configuration here very shortly. So we'll be talking a lot about that in upcoming slides. A final example, let's look at uranium. Uranium, when it is neutral and equal number of electrons and protons, it fits with 92 total electrons. It's getting way down there in the table, as you can see. So again, we'll use the Aufbau principle, occupy the lowest energy orbitals for this element, and just populate them with the maximum they can hold until we reach 92 electrons. And I will just go triangularly through the orbitals, putting the maximum number in, keeping track of the number of electrons I'm adding into the orbitals. And when I am done, I would end up, as you see there, with the final orbital 5f4. Now what it turns out is we will see that there is correlation between this triangular formulation and the periodic table location based on which particular orbital is being filled. But in the case of uranium, the triangulation formula does not exactly match what we will see comes out from the predicted location in the periodic table. This is because this triangle rule really is not foolproof. It does not work perfectly, particularly when you get to larger or heavier atoms with many electrons. The triangle rule breaks down in a number of places. So what I want you to take from the triangle rule is that it's a trick that we can use to mostly predict, particularly for the first several rows of the periodic table. But after you get past row 5 and 6, and particularly when you start putting in d electrons, of just a few d electrons, this can break down dramatically at those locations as well. So the take home that you should get from this is that this is not foolproof. It's only a quick and dirty rule of thumb, and a little bit more trickiness goes into these in general, but this is a simple rule that we can apply to get a very good idea of the order of filling of the electrons. Let's look at a particular example of this violation of this triangle rule that I was talking about on the previous slide. There are many instances of violations of this in the periodic table. So again, remember, you should just think of the triangle rule as something simple that we will use, but not necessarily written in stone to guarantee the correct electron configuration. For example, let's take the case of chromium. Chromium has 24 electrons total, and so if you draw out the triangle structure, you'd get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. That would be exactly what you would need to do to get to the correct structure for chromium. But in actuality, what it turns out is that chromium populates its orbitals at the core level exactly as shown. So through the 3p6, which are the core electrons, they are populated as shown in the triangle rule, but then at the valence level, instead of being 4s2 3d4, it's actually 4s1 3d5. And the reason behind this violation of the so-called off-bow principle, that's what it seems to be doing, we're violating the off-bow principle, but the reason is because Hund's rule wins. Hund's rule, which says that you want to maximize the spin, you want to put the most spins of the same form before you begin to doubly occupy, because of the closeness of energy between the 4s and the 3d, it's able to promote one of the 4s electrons into a 3d instead of spinning it opposite as it would have to do in the 4s. It spins it in the same direction in the 3d, and that again lowers the energy enough so that this is a favorable way for these electrons to be arranged. And this is not what would be predicted by the off-bow principle using the triangle rule. So there are lots of violations of using that. This is not the only example of such. There are many others that we would have to keep in mind when we're doing things with the triangle rule. Let's look at a definition of what is known as an isoelectronic atom. Isoelectronic atoms are atoms that have the same number of electrons. Well, in actuality, we can have isoelectronic atoms and ions, as which we should maybe more correctly see. And we show here three isoelectronic atoms and ions. The neutral atom is silicon with 14 electrons, which populates its electrons as shown. This one doesn't have a violation of the off-bow principle or the triangle rule. It would be 1s2, 2s2, 2p6, 3s2, 3p2. That would be the form for silicon. But if I now made the anion aluminum -1, neutral aluminums have 13 electrons, so it would have exactly the same electron configuration as would chlorine +3, which chlorine's neutral begin with 17 electrons. When you make it a +3 cation, it would also have 14 electrons, and they would populate exactly the same orbitals above the nucleus. Now remember, the nucleus of chlorine still has 3 additional positive charges, so that's going to put the locations of the 14 electrons on chlorine +3 in different spots than the location of the 14 electrons of silicon, as well as the 14 electrons of aluminum -1. So they will have differences in regard to how far out and how far in these orbitals are, depending on how much attraction they feel for the nucleus. But in any event, they are isoelectronic in the sense that they have exactly the same electronic structure. Let's look at what electron configurations have to say about excited states and the emission of light that an excited state experiences as it falls back to the ground state. Let's take the case of sodium, which is a practical example due to this particular emission that is used in lighting and security lighting and interstate lighting. If I take the ground state or lowest energy state as shown on the right for sodium, for those 11 electrons of neutral sodium, it'd be 1s2, 2s2, 2p6, 3s1. Now, if I stimulate the ground state with electricity, I can promote an electron from the ground state to an excited state. So the electron that which is originally in the ground state in 3s1 is promoted to 3p1. But now, as you move away from the electricity, that stimulated electron can't remain in the 3p1. It must return to its ground state location. And in order to do so, it must shed the energy that it possesses, and it sheds it in the form of yellow light that we can see of wavelength 580 nanometers. So this is the characteristic light you see off interstates and behind warehouses for security. Very intense, very bright yellow light, which only takes a little bit of electricity to stimulate, yet provides very bright light from it. So this is an example of the emission of light and showing the electronic configuration that undergo a transformation as that yellow light in this particular instance is emitted. let's look at what electron configurations tell us about light that is absorbed by elements and then reflected and showing the complementary color upon reflection. So let's take, in this case, copper, and again, we'll look at copper plus 2. And copper plus 2 is a cation that is deficit of 2 electrons from the normal position of the copper element. So in the ground state of copper, I would have populated the lowest available orbitals. I would begin 1s2, 2s2, 2p6, go to 3s2, 3p6, 4s2, and 3d7. That's the ground state of copper. Now, when light from a source external to the copper shines on copper cations in solution, the copper cations love to absorb the orange light. The orange light is of wavelength 620 or so. So the copper atoms in solution absorb that orange light. And when they do so, it stimulates an electron from the ground state, and in particular the 3d orbital. It moves one of those electrons up to an excited state. As you see where the arrow is going to the excited state, all the orbitals are the same except one of the 3d electrons is promoted to 4p. Now, as long as the light shines on this sample, that electron will remain in that 4p orbital. When you turn the light off, it will cascade back down to the 3d, leaving 7 electrons in the 3d. So as long as the orange light stimulates this process, light reflected from the bottle will be the complement to the orange light that's being absorbed. So blue light is reflected off of the solution to your eyes as the orange light is absorbed, keeping the electron stimulated into this particular excited state for the copper plus 2 cation. Let's look at how to write abbreviated electronic configurations. What we've noticed is if you get to really large number of electrons in an atom, you have to write a ridiculous number of orbitals down and put a bunch of 1s2, 2s2, 2p6, 3s2, 4, on and on and on it goes. So what chemists have designed are abbreviated electronic configurations which eliminate the core electrons. And eliminating the core electrons means writing compactly a representation for all electrons in filled energy levels. This requires using elements at the end of the rows of the periodic table which delineate and differentiate the point where you switch from core electrons to valence electrons. So the column of the table, column 18, highlighted in red here, is a delineation between core and valence electrons. Again, we like to know more information about valence electrons because of the fact that these are the ones that are very often available for energetic purposes in chemical reactions and things of that sort. So we're going to use the column 18 elements to help to abbreviate the electron configurations, as we will see how to do on the next few slides. Let's look at the electron configurations of the group 18 elements, at least the first 5 of them. Helium, neon, argon, krypton, and xenon. They're written out there. Helium goes to 1s2, and then you'll note that to go to neon, you have to go through the second principal quantum number, 2s2, 2p6. Argon includes the third principal quantum number through the p orbital. Krypton includes the fourth principal quantum number through the p orbital. And xenon includes the fifth through the p orbital principal quantum number. These are the core electrons for elements past this particular row, and chemists for a long time designated these as the K, L, M, and N shell of electrons. The K shell consists of 2 electrons, complete up to helium's 1s2. The L shell has a total of 10 electrons in the L shell, including the 1s and the 2 orbitals of the 2p. The M shell has an additional 8 electrons to give 18 electrons in the M shell. And the M shell includes a total of 18 electrons, as I said. The N shell has a total of 36 electrons in it. Now, again, what we're really going to do is use these, as we will see, as a trick to populate many electron atoms in an abbreviated form. Let's look at how we would write an abbreviated electronic configuration. Let's begin with a simple case where you probably wouldn't abbreviate it to begin with, but we'll look at the case of beryllium. And beryllium has a full electron configuration, 1s2, 2s2. We will eliminate the core, so we will identify everything in the first completed energy level, which is energy level 1, indicate that by the element, the noble gas element in column 18 at that end of that row, which is helium. So I'll write helium in brackets, then include all the valence level electrons, which would be the 2s2. Now, let's take a little more tricky example. Let's go to antimony with 50 electrons. I would use the triangle rule to figure out how to populate those 50 electrons. And I see that that would end at 5p3. Now, in order to abbreviate the configuration, since level 5 is not all the way completed, I would find the level that is completed out to the end of the p's that are completed, and that would be the last completed p is 4p, 4p6, and 4p6 occurs at the element krypton. So I would just, instead of writing all the level 1, level 2, level 3, and level 4 electrons that antimony has, I will just put krypton as its abbreviation, and then I will put all subsequent electrons beyond that, and that would be the 5s2, 4d10, and 5p3 as the outermost electrons where all the action may occur in the chemistry of this atom. Finally, I look at a cation of americium. Americium itself actually has 95 electrons. Americium plus 2 has 93 electrons. Doing the triangle rule and writing out all electrons present in americium would get me all the way out to 5f5 and would have a huge number of electrons present. But what I would do is find the last p orbital, which is the 6p6. That designates all the elements in column 18 that end in the p row of that particular core above them. And the row 6 p element, end of p row element, is the radon element. So I would truncate all those many myriad of filled configurations and just abbreviate the core as being equal to the core of radon, and then only have the partially being filled ones past radon, which are the 7s with 2 electrons and 5f with 5 electrons.